Welcome to my channel. Today I want us to look at more examples on matrices. We've been looking at matrices and we've looked at quite a number of examples. So today again we'll look at more other examples. So let me begin with examples. Now the first example that I want to look at is the notion of equal matrices. We already talked of when do we say that matrices are equal, and we say that matrices will be equal if they are of the same size and the corresponding elements are the same. So for example, find the values of x, y, and z for which x plus 4, 3y minus x, z plus 3, and 4a plus 7 equals to 3 negative 5 and then 5 3a. So the question is, we should find the value of x, the value of y, and the value of z, and the value of a, and even a. Find also a. So let me say find x, y, and z for which these two matrices are equal. Now we can all see that these matrices are of the same size or order, that each of these has 2 rows and 2 columns. Now, so they will be equal if this first element, x plus 4, would be equal to 3. Now, so if x plus 4 equals to 3, then this means that x will be negative 1. Negative 1 when 4 crosses the equal sign. This matrix will also be equal if this second element, 3y minus x, will be equal to negative 5. Now, we already know what x is. So this means that 3y plus 1 should be equal to negative 5. So you see this is negative 1, so it's minus 1. Minus and minus will give us positive. That is why you see this. And so this, if this one would cross the equal sign, it will be negative 1. So this will be negative 5 minus 1. So that means that 3y should be equal to negative 6, or that y should be equal to negative 2. Now, so this element will be equated to that. Then the second element to this. Now z plus 3 should be equal to 5, and this would mean that z will be 2. And what about this one? We've been told that 4a plus 7 is 3a. Now, if this 3a were to cross the equal sign and 7 crosses to the other side, you would have that a the same as negative 7. A would be negative 7. So you have the value of a, you have the value of z, which is 2, and you have the value of y, which is negative 2, and you have the value of x, which is negative 1. And what we used is the notion of equality of matrices. That matrices will be equal if they are of the same order and their corresponding elements are the same. Now let's look at another example. So I can say that was example A. So now we look at example B. Now, so what is example 2? Let me go to example 2. What it says is that if A is this matrix 2, 2, 1, 3, and B is this other matrix, which is 1, 2, and negative 2, 1, find AB and BA. Now, the question just wants us to multiply these matrices. And remember the other time we said that we can multiply matrices if the columns of the matrix on the left side, in this case A, is the same as the rows of the matrix on the right side, in this case B. So we're looking at the columns of A here, and looking at the rows of A here, rows of B. If these columns are the same as these rows, then we can multiply these matrices. But if they are not equal, then we cannot multiply. Now, for our case, we can multiply A and B. So let's just do that. A and B. So AB will be 2, 2, 1, 3 multiplied by 1, 2, negative 2, 1. And remember how we do this. It's this row times this column, then again this row times this column, and then this row and this column, and this row and this other column as you add. So 2 times 1 would be 2, and then 2 times negative 2 would be negative 4. So this 2 times negative 4 will be giving us negative 2. Because this will be 2 minus 4. And then this element times this will be 4, and this element times this will be 2. So when I add 4 and 2, that will be 6. Now we are done with the first row and each of the columns. Let's come to the second row. 1 times 1 would be 1, then plus 3 times negative 2 will be negative 6. So 1 plus negative 6, that will give us negative 5. Then 1 times 2 will be 2, 3 times 1 will be 3, so 2 plus 3, that will give us 5. So this is AB. This is AB. What about BA? What about BA? So 1, 2, negative 2, 1 multiplied by 2, 2, 1, 3. And what do we get? 1 times 2 is 2, and then 2 times 1 is 1. So I have this 2 times that 2, which is 4. Then this times that will be 2, this times that will be 6. So 2 plus 6, that will be 8. Then this negative 2 times this 2 will be negative 4. 1 times 1 will be 1. So negative 4 plus 1 will give us negative 3. Then negative 2 and 2 will be 4 negative, and this will be 3. So when we add those two, we get negative 1. So 4, 8, negative 3, negative 1 as the result. So we know how to multiply matrices, and that's how we do. Whether it is a different order, whether it's 3 by 3 matrix or 4 by 4 matrix, and so on. Any order of the matrices here given, we can multiply using the same machine. And of course, I just want to remind you what I said last time. What I said last time is that if A is an M by P matrix and B is an P by N matrix, then we can multiply these matrices because you can see the columns here are the same as the rows here. So what will be the order of AB? The order of AB would be M by N matrix. So I take the rows of A, the one on the left, and then the columns of the one on the right. And so this gives me the order of the new matrix. And we did that last time. We did an example. For example, if I'm given 1, 2, 3, and I'm multiplying this by 2, 1, 1, 1, 1, 0. This is a 1 by, this what is the order of this? 1 by 3. 1 by 3. And the order of this 1, 2, 3. 3 by 2. So the rows are 3 and the columns are 2. So I expect that this product should be of order 1 by 2. The product 1 by 2. So the rows of the matrix on the left and the columns of the matrix on the right, 1 by 2. Let's just see. This will give me 2 plus 2, which is 4, plus 3, which is 7. Yeah, that is 2 plus 2, which is 4, plus 3, which is 7. And this other will be 1 plus 2 plus 0, which is 3. So you can see these are 1 by 2, 1 by 2. That is the order of this matrix. So this is a very important point, that if you are given two matrices which are compatible, those which you can multiply, you are able to know the order of the product. Now let's look at another example. That will be our example 3. So I want us to look at a very easy example here. We looked at similar case before, and the question is, verify that the determinant of 1, 1, 1, x, y, z, y, z, zx, and xy is same as the determinant of 1, 1, 1, x, y, z, x square, y square, z square. So this is the question that just shows us that the determinant of this matrix here is the same as the determinant of this matrix. Now if you were to try to do this determinant and then do this, you will find that they are equal actually. But that is not the way I want to do it. The way I want to do it, I just want to work on this determinant, simplify it, the one on the left, and see that I have this, what is on the right. So I begin with what is on the left. I begin with what is on the left. I want to work on it and see whether I can get what is on the right. So using the left side, using this, the determinant of 1, 1, 1, x, y, z, y, z, zx, and xy. I want to multiply this row by x, this row by y, and this row by z. So I want to multiply, and you know that if I multiply, remember what we said about the properties of determinants. We say that if you are given a determinant A, a matrix A, and then you multiply any of the rows by a constant alpha, the new determinant will be the old determinant times alpha. What I mean is this: if A is this matrix 2, 1, 0, 1, then if I was to multiply this row by 2, if I was to multiply that row by 2, 2 is a constant, I get 4, 2, 0, 1. So what will then happen is that the determinant of B will be the determinant of A times 2. Let's see what is the determinant of A. The determinant of A is just 2 minus 0. So I expect that the determinant of B will be these 2 times the constant we multiplied. So that would give us 4. And that's what you see here. So that means if I want to maintain the determinants, after multiplying this by constant, this one, after multiplying 2 by A by constant 2, if I want to maintain this determinant, I must divide here by the constant I multiplied with. And that's what I want to do. That's what I want to do. So I've just said that I want to multiply the first row, multiply row 1 by x, row 2 by y, and row 3 by z. I want to do that. Now, when that happens, what do I get? So, I've multiplied by x in row 1, y in row 2, and z in row 3. So, I have to divide so that I maintain the determinant. That the determinant remains the same. So, this will give me x squared, xyz, and this one give me y squared, xyz, and this will give me z squared, xyz. If I multiply this by z, that's what I get. If I multiply this by y, that's what I get. If I multiply this by x, this is what I get. Now, so I've noticed here that there is a common factor along the third row, and the common factor is xyz. So I can factor it out. So factor out xyz. Factor out xyz, and you see it was here, xyz was here. So this is the one I'm factoring out. So when I do that, what I will have will be x, y, z, x squared, y squared, z squared. And this will be 1, 1, 1. Now, I can now interchange. I'm looking at what I want to achieve. What I want to achieve, I have 1 in the first row, I have x, y, z in the second row, and then I have x squared, y squared, z squared in the third row. That means I only need to interchange these rows, not the columns. I have 1, 1 in the first column, x, y, z in the second column, and then x squared, y squared, z squared in the third column. But look at what I have. That means I need to interchange some of these things, but you remember outside the bracket here, outside this will cancel and I'll have 1. Now, let me just remind you what happens when you interchange rows or columns. When you interchange rows or columns, the new determinant becomes the old determinant times -1. Times -1. So the sign of the determinant changes. So if the determinant was positive, it becomes negative. The new determinant becomes negative. And if the old determinant was negative, the new one becomes positive. We just multiply the older one by negative. Now, so I want you to change column 1. I want you to change column 1 and column 3. And also interchange. Let me do that one first. And so that gives me negative outside because I'm interchanging columns. Negative comes outside. 1, 1, 1. X square, y square, z square. And this other one is x, y, z. Now, I also now want to interchange. I now want to change column 2 and column 3. So interchange column 2 and just write clearly. Let me erase some space here. Create some space here. In fact, create this. Let me open some space here. Create some space here. Now, so I want to change column 2 and column 3. Let me just write what I want to do. I want to interchange column 2 and column 3. So what do I get just before that? There's already a negative outside. So when I interchange these two other rows, these other columns, then another negative again coming outside. And so what I then have would be 1, 1, 1, x, y, z, and then x square, y square, z square. X, 1 times negative, 1 times negative, 1 to positive. So what I now have is this 1, 1, 1, x, y, z, x square, y square, z square. And this is what I wanted to show. I wanted to show that this determinant is the same as this determinant. And I simplified this determinant here to arrive at the determinant on the right side. And this is what was required. This is what was required. You are needed to show that this determinant is the same as this determinant. And we just showed that. Now you go through this example and the other examples I showed in my previous video on how to simplify some of these things. Of course, you may want to do it by row reduction. You want to do it by row reduction and you would still get the same thing. Now let me look at another example. And the example I want to look at is, that should be 4. Example 4. Show that this one is easy. We looked at the same last time, a similar one, but I just want to look at a different approach. X, y, z, and x square, y square, z square. Show that it's the same as y minus z, and then z minus x, and then x minus y. Now, so for me to do this, I have to remember what I want to achieve, and I'm looking at this equation here, at this determinant, and I'm seeing there is x minus y. There is x minus y. Okay, that will guide me, and then there is y minus x, y minus z. So what I see, for me to achieve this x minus y, I'm subtracting this row from the earlier row. And then for me to achieve this y minus z, I'm subtracting the third row from the second row. So let me just do that. Solution, just do that. What I have is the determinant of 1, 1, 1, x, y, z, and then x square, y square, z square. And so what I'm saying is, okay, these are supposed to be vertical lines to mean a determinant. Now, so what I have said is that I will take, to get my new row 1, to get my new row 1, I have taken the old row 1 minus old row 2. So I have x minus y. Then to get my new row 2, I've taken the old row 2, then minus the old row 3. Let me do that and see what I get. Row 2 from row 1. 1 from 1 gives me 0. Y from x. Y square from x square. And then this from that, I have this from that, I have 0 here. I have y minus z, and then I have y square minus z square. And this one remains, it is 1 z square. Now, so we can now find the determinant along this column. Along this column. So, remember this is positive, negative, positive. That determinant is 1 multiplied by, when I delete the row of 1 and the column of 1, what I'm left with is x minus y, x square minus y square, y minus z, y square minus z square. That's what I'm left with. Now, so let me just simplify this. This is the same as 1 into. I can try to simplify this. This is x minus y, and this will be x minus y, x plus y. Although it's not always the case, but let's just do it to make our work easier. It's not always the case that for matrices x square minus y square will give us this. Now, so, and what about this other part? It will be y minus z, and this one will be y minus z multiplied by y plus z. Now, so you notice that the first row has a common term, x minus y is common, and the second row has a common term, y minus z is common. So let's just factor out the common terms. X minus y is a common term in the first row, and y minus z is a common term in the second row. So x minus y will go here once, and it will go here x plus y. And then y minus z will go here once, and it will go here y plus z. Good, so let me create some space to do the remaining part. I just want some little space here to do the remaining part. Now, so what is this? Outside the bracket, what we have is x minus y multiplied by y minus z. And inside the bracket, inside this determinant, we have the determinant, this minus that. So that is y plus z minus x minus y. So y minus y equals 0. So what I have now is x minus y multiplied by y minus z, and this other bracket we have z minus x. So you can do some little arrangement, little rearrangement to get what we want. Some little rearrangement gives what you want. I can begin with this y minus z, followed by z minus x, and follow this by x minus y as required. So that is just a little rearrangement. That's how we do it. That's how we do it. I want to come back to this point I was explaining there. Just want to show you something before I proceed with the next example. There's a point I was explaining there, and it's very important. But I say it will work for this type of question, but not everywhere. It will not work everywhere for matrices. So the question that I was explaining there is this. The question is x squared minus y squared the same as x minus y, x plus y, the same as what is this? X plus y for matrices. Is it always the case? Is this the same as that? And what I'm saying is that not always. My answer is not always. Not always. For some matrices it will be true, but not for all matrices. Let's see. Since what is my reason? That if I were to take x minus y multiplied by y plus, can I get this for matrices? The first one will give me x squared if I multiply it. The second one will give me xy, and this will give me minus yx, and this will give me minus y squared. But this part, is this part equal to 0? Not always, because matrices are not necessarily commutative. In the example that we saw earlier, we saw that AB was not equal to BA. So for some matrices, AB will be equal to BA. That's why I say not always. Because for other matrices, AB will not be equal. So for this kind of matrix, it's not true that this part will give you 0. But for other matrices where this part gives you 0, so you can see that it will be true that x squared minus y squared would give you that. But for matrices where this is not the same as this, then you can never get x squared minus y squared, because there will always be something here. This is not always equal to 0 for matrices, because matrices are not commutative. Matrices are not commutative. Are not, let me say, always commutative. Are not always commutative. Because you would have others that would be equal. that AB will be equal to BA for other matrices, but not for all matrices. Okay, let's proceed with our example. So you've understood why I said that this part here is not always equal to that of matrices. But then I say that for this example that we are doing, then it will work for this example. Okay, I want us to look at another example, very easy. There is an example, and the one that I want us to look at is, I think it should be example 5. And it's shown that, just erase this, show that this matrix 1, -3, 4, 2, 7, 8, 1, 3, -10, 3, 4, 14, 3, -9, 12, 6 is singular. Show that this matrix is singular. A very important thing here is the word singular. You know what it means. The word singular means this is a matrix whose determinant is 0. So the question is saying, show that this matrix has a determinant of 0. That's what the question is saying. For example, I say show that it has no inverse. So if it has a determinant of 0, then it has no inverse. Because inverse is 1 over determinant times adjoint. So 1 over determinant, when the determinant is 0, then that 1 over 0 does not give us something. Now, so the question is, show that this matrix is singular. In other words, find the determinant of this matrix and show that that determinant is 0. Let me do my solution here. So my solution here, first of all, I discover that there is a common term in row 3, so I can put it outside. There's a common term in row 3. So row 1 remains what it is. Row 2 remains what it is, 7, 8, 1, 3. And then this one remains as -10, 3, 4, 14. And this one has a common term which is 3. Let me divide through by 3. I would have 1, -3. And this would be 4. And this would be 2. Now, so we said earlier that if a matrix has 2 rows which are identical, or 2 columns which are identical, then the determinant of that matrix will be 0. Because I can see this is 3 times the determinant of this, but this row and this row are identical. Row 1 and row 4 are identical. So that means the determinant is 0, and hence proved. So we proved that this matrix is singular, because we've already found that the determinant is 0. So you don't need to do a lot of work here to get determinant. Just check and see whether you can use 1 or 2 of the properties we learned. Like you look at this. When I discovered that there's a common factor here, I put it out, and then I looked at this row and this row, and they were the same, and so I applied them the property that whenever you have 2 rows which are identical, or 2 columns which are identical, then the matrix will have determinant of 0. So again, you can see that is a very good question. Let's look at another very good question here. Just before that, I want to define something for us. The term symmetric matrix. Symmetric matrix. So when we say that a matrix is symmetric, we already learned about identical, non-equal matrices. We learned about just before this, we looked at singular matrix. Matrix whose determinant is 0. And when we say that a matrix is symmetric, so a square matrix A, a square matrix, it must be square, is symmetric or is said to be symmetric if it equals to its, if A equals to its transpose here, then we say that this A is symmetric. If it equals to its transpose, e.g., if we have matrix A which is ABC and B, D, E, and then C, E, F, what is the transpose of this? It's symmetric because the transpose of A is what? What's the transpose of A? Let's make the rows be the columns. First row becomes the first column, second row becomes the second column, and the third row becomes the third column. So you can see that A equals to its transpose. A equals to its transpose. So A here is a symmetric matrix. Symmetric. So we say that matrix is symmetric if that matrix equals to its transpose. And I've shown you that example. So it's good to know the types of matrices actually. Now let's look at an example. That should be example 6. Find x if x plus 3, 8, 2, x minus 3 is singular. Find x if this matrix is singular. So this is easy. We already know that the determinant of a singular matrix is 0. So let's just find the determinant and equate it to 0. Equate this matrix, the determinant to 0. So this will just be x plus 3 multiplied by x minus 3, then minus this other diagonal, which is 16. So what does this give you? Oh, equals to 0. What does this give you? This would be x squared negative 3x, that gives us 0, negative 9, negative 16 equals to 0. So what is this? X minus 25 is 0. Now x squared minus 25 is 0. That means that x is positive or negative 5. X is positive or negative 5 if this matrix here is to be singular. So again, that emphasizes the notion of singular matrix. It emphasizes that to us that is a matrix whose determinant is 0. Another example, example 7. And example 7 says, show that this okay, let me just change the question. Show that this matrix 115, 118, 120, 116, 119, 121, 118, 121, 123 is singular. Show that it is singular. So that means show that its determinant is 0. And let's see the workings. So the determinant, let's find the determinant of this matrix. 118, 120, 116, 119, 121, 118, 121, 123. You can use any method that you know to find the determinant of this matrix. But for me, I want to employ some knowledge that we know about determinants. I know that when I add a row to another row, the determinant of the new row will be the same as the determinant. No, the determinant of the new matrix will be the same as the determinant of the old matrix. And that therefore means that subtracting a row from a row or a column from a column has no effect on the determinant. Let me do that. Let me subtract row. Let me get row 2 by subtracting the current row 2 minus row 1, and get row 3 by subtracting the current row 3 minus row 1. Because subtracting a row from a row has no impact on the determinant, it remains the same. So I have 115, 118, 120. When I subtract this from that, I have 1, I have 1, I have 1. And subtracting row 1 from row 3, I have 1. I have 3 here, I have a 3 here, and I have a 3 here. Now, I also notice that there's a common term along the third row. So I can factor it out. I can factor it out. You have 115, 118, 120, 1, 1, 1, 1, 1, 1. When I factor 3 out, I've discovered that row 2 and row 3 are the same. And there's a property that says that if two rows are identical, then the determinant will be 0. So this is 0. And therefore, this proves that the matrix given to us is singular. This proves that the matrix that is given to us is singular. I've not said that this is the only method we can use. You can also want to just find the determinant using expansion. When expand along this row, or along this column, or along any row, or along any column, and find 0 as the answer of the determinant. Find the determinant as 0. So you just find out the determinant of this matrix. For me, I used the properties of determinant here, but you can use any other method. The only important thing is that find the determinant, and if that determinant is 0, conclude that the matrix is singular. Let's look at another example. That should be, I don't know whether it's example 9 or 8. No, the numbering is not very important. You can number it later. Show that the determinant of S squared AB SC negative AB B square BC and SC negative CB and C square is 4S square B square C square. Show that this determinant is that. And as I said, we have so many ways of doing that. There are so many ways. So the first thing that I do is for me to discover that each of these rows has a common factor. So for instance, there's A which is a common factor there, there's B which is a common factor on this row, and there's a C which is a common factor there. So let me factor out the common factors. The first row has A, the second row has B, the third row has C as the common factors. Let me put them out. A goes in the first row as A, B, C. B goes in the second row minus A, B, C. And C goes in the third row, A minus B and then C. Now, so I want to get the determinant, this is the determinant. I want to use row reduction. I want to use row reduction, but I want this A to be the only non-zero element in the first column. I want this to be 0 and this to be 0. So what I mean is, I want to get the second row by taking the original second row, the current second row, plus the current row 1. And then the third row, I want to get the third row by taking the current third row minus row 1. So when that happens, what do we get? What do we get? So we already have our constants outside. Now, the first row remains where it is. Add it to row 2 and you have a 0 in this position. Add this to that, you have 2b, and add this to that, you have 2c. And then subtract row 1 from row 3. This minus that gives me 0. This minus that I have minus 2b, and this minus that I have 0. Now you can find determinant along this column, but I don't want to do that. I want to use row reduction. So I want this to use this element to create a 0 in this position. Use this to create a 0 below it. So what will I be doing? What I want to do there is that I want to get row 3 by taking the current row 3 plus row 2. That's what I want to do. And so what does that give me? What does that give me? I already have ABC outside. ABC. Row 1 remains where it is. Row 2 remains the way it is. Add row 2 to row 3 and you have a 0 here. You have a 0 here. And you have 2C. We now have a diagonal matrix, or no, triangular matrix. We now have a triangular matrix, and whenever we have a matrix like this, the determinant is given by multiplying what is on this main diagonal. What is on this main diagonal? We already have ABC here, and then the determinant of this matrix is the product of the main diagonal. So let me create some space and so so that we can finish our work for this question. So we already have ABC outside. So the determinant of this matrix is A times 2B times 2C, which is 4ABC. 4ABC. When you multiply this, what you get is 4A square, B square, C square as required. So this is what we wanted to show. We wanted to show that the determinant of that matrix was this. That's what we've done. I've just used row reduction. You would have used any other method. You would have used another method from this point. From this point, you would have used another method. Let's see how you would have done it. Although we already have the answer. So supposing I'm here, how else can I proceed? And we know how to proceed if we are at this point. That we can find a determinant along a column that has more zeros. So we already have A outside. Let me just erase again. Erase this part, and I want to complete at this point also. Remember, we already have the answer, and we're just looking at another way that we would have done it. Another way that we would have done it. The problem is whenever I use two ways to do the same question, people again ask why I used two ways. And I always say that I'm using a way to show the alternative way. But I've already shown one way, so I want to show the alternative way. So there's no problem showing the alternative way. It doesn't mean that question must be done using two ways. It only means that you can proceed with one way or another one. Now, so I want to proceed from here. So I already have ABC outside. And I want to beat along this diagonal. So that will be times A times the determinant of the matrix that remains when you delete the row of A and the column of A. When you delete the row of A and the column of A, what you get here is 2B, 2C, negative 2B, and 0. So this would be, let me just multiply this. I have A square BC multiplied by the determinant of this matrix is negative 2. This is 0. This is 0 minus, and this is minus 4 BC. So this is just A square BC times this minus and that will be positive 4 BC. What does this give us? This is 4A square B square C square. So this is what we needed. This is what we needed. So we have shown that we could have proceeded in any of the ways, either this or the any one. Okay, let's look at another example. And the example is, that is example 9, using row reduction. Using row reduction, find the determinants. Find the determinants of part A. I want the determinant of 2, 3, 7, 4, 5, 9, 6, 0, 3. Want the determinant of this. I want to use row reduction. So solution, I have 2, 3, 7. The question asks me to use row reduction, so I'll stick to that method that has been asked for. I'll stick to the method. because the question, the method is row reduction. Now, so that means I want to remain with the diagonal here, and below it I want zeros. I want this diagonal to remain, and to the left of this diagonal I must have zeros. So that means I should use this tool to create zeros below it. So how do I get a zero here? By taking, in fact I should have begun by, because I've discovered that this column here has a common term which is 2. I should have begun by factoring 2 outside. But since I've already started, let me just continue. So I need to multiply this row by 2 and subtract from row 2. So multiply row 1 by 2 and subtract from row 2 to get the new row 2. So 4 minus 4 is 0. 5 minus 6 will be negative 1. 9 minus 14 will be negative 5. I also want a 0 in this position. So I would multiply this row by 3 and subtract the result from row 3 to give me the new row 3. So that is 6 minus 6, which will be 0. 0 minus 9, which will be negative 9. And 3 minus 21, which will be negative 18. Now at this point you can even want to divide by negative 9, put negative 9 outside because it's common here. But that's not what I want. What I want is, I just want to create a 0 in this position using this negative 1. So in other words, I want to multiply row 2 by negative 9 and add that result to row 3. Multiply this by negative 9 and add the result to row 3. Row 1 and row 2 remains where they are. Now 0 times negative 9 plus 0 will be 0. Negative 1 times negative 9 will be positive 9. Add it to negative 9 and that gives me 0. Negative 5 times negative 9 will be positive 45. Positive 45, add it to negative 18 and that gives us 27. So that means the determinant here is the product of this diagonal, which is 54 negative. I've used row reduction. So that means you come up with this diagonal, you multiply the elements along that diagonal to give you the determinant that is required. Let's look at part B of example 8. And that one I'll just leave it as exercise for you to do. And leave it as exercise. And then of course give you the answer. But I want you to use row reduction. So part B, I want you to give me the determinant of 1, 0, 3. Then 4, 1, 7, 4, 1, 7, and 5, 3, 2. 5, 3, 2. I want you to give me this determinant, and my answer to this is 2. Now you must use row reduction because that is what the question wants. Of course, there are so many other ways of doing this question, and the question wants you to do using row reduction. And that brings us to the end of today's examples, worked examples. Thank you for having joined me from the beginning to this end. And if you've not subscribed, remember to subscribe so that whenever I upload a video, you can easily get it. Thank you.